and send you to the first problem on the practice quiz today. So today we're going to kind of go more in depth into dot products and cross products, particularly the cross product. Go ahead and do number 1A.
That.
Hi. Hi. Somebody's got their mic open. I can hear. Small child. Okay, 30 seconds more. Okay, so we shall do this. Now we set this up is to remind us. So we don't have to memorize this kind of awkward formula. We take ijk. The bars mean the determinant of the matrix. If you put little tiny sideways parts, that would be the matrix itself. The first one must be the first row of these two bottom rows. And the last one is the last row. And then you can go across the top row. Normally when you take the determinant, you can go across any row that you choose. As long as you keep in mind that this term is associated with a positive coefficient, plus, minus, plus, and alternate. Plus, minus, plus, and so on. But if we go across the top row, it's I times the determinant of the 2 by 2 that's left over. So we knock out that column and that row. Opposite sign as you move to the next element. J. Opposite sign, K. And this is going to be I. 8 minus 1 is 7. J. 4 minus 3 is 1. 2 minus 12 is negative 10, which could also be written in vector format. 7, negative 1, negative 10. Okay, give me a little bit of feedback on 1 part A. Let's go to 1B. State a possible meaning for the answer you got in A cross B. And if you're feeling up to it, give another possible meaning. If you're feeling up to it, just keep on going. As many possible meanings as you can for this vector. Okay, now in your Discord group, type in your answers and look to see what other people got. We'll see if together we can come up with lots of different possible ways to interpret this answer. Alright, so group 2, give me one way, a possible way you can interpret that answer.
I said that the torque, when there was a radius that was represented by the vector A and a force that was represented by the vector B.
Alright, you are really close.
Did I have them flipped? Is it the force times the radius?
I think so.
Okay.
It's the turning effect, or the now what gives you that torque or the turning effect? Is it this vector, or what about this vector?
That vector represents the torque.
The vector itself represents the torque. How about the amount of the torque? How do we get the amount of the torque from this vector?
That would be the magnitude of that vector.
Right. When we're talking about the torque, we're usually talking about the magnitude of the vector. So, the magnitude of this vector and that's going to be 149, 150. And we take the square root of the sum of the squares. And the square root of 150, let me put that into my calculator real quick. It's a little more than 12.
5 root 6?
Yeah, about 12.25 is the amount of rotational force that A exerts on B. rotational force that we can call this a force, and this an arm. Now the force could be pushing on, and the arm could be a wrench. Okay. And all right, if we were in two space, that we were doing is we could verify it with a quick picture, and because does it rotate, the vector itself would tell us the direction of the rotation. In three space it's a little harder to see, and to see that I'm not misremembering this, but I'm pretty sure that it is the first one exerts on the second one.
The book says that the torque equals the cross product of the radius times the force. There's the cross product of the radius and the force.
And the torque is the magnitude of that, or just the vector?
It says that the torque equals the magnitude of R cross F.
Yes. So this is the torque. Because that's R cross F right here. We're imagining one of them's an R. Oh, and it's saying, all right, but the magnitude doesn't matter the direction. R cross F, F cross R, they're going to give you in opposite directions vectors, but their magnitude will be the same. So they didn't have to have the order of it correct for that. But I think it's this force and this arm that the cross product, I think, is what I remember. But well, I can verify that before next class, or during a break while I do a simple problem. All right, so that was, so it's telling us that, now, how much torque we have is kind of relative, this number, kind of relative to what? Well, the maximum amount of torque that you could have gotten is by putting these two perpendicular. And that's when theta is 90 degrees, and that's when you're going to get the maximum torque. So let's just put this. Max torque possible is magnitude of A times magnitude of B times the sine of theta when theta is 90 degrees. And then you're going to get 1 for this portion. And this is going to be the magnitude of A is 4 plus 16 plus 1, which is square root of 21, times 9, 10, 14. And if I take those two and multiply them, and then raise to the 0.5 power, I'm going to get
7 root 6?
Yeah, 17.2 approximately. So the maximum torque possible was 17.2, and we got pretty close, reasonably close, 12.25. So these two have a good deal of them is perpendicular. Now, hard to visualize it in 3 space, but let's take a quick 3D image. Let's go with, I have it here. So I'd go, so here's my X, Y, Z. I go 2 into X, 4 in the y, and then 1 up. Okay, and then the b, I'll do that in green, 3, 1, and 2 up. And you see the green vector and the red vector are not really pointing in the same direction. There's a good deal of perpendicularity to them. And that this, now the A is the red one. How much does that turn this one? Is now the, alright. Let's go next. That was group 2. Group 1, did you have any another possible interpretation that's different than this one?
Let's see, we have basically that vector that we calculated,
Yes.
A crossed with B,
Yeah.
is a vector that is orthogonal to both A and B.
Aha.
So it's like a measure of how orthogonal two vectors are with each other as well.
The magnitude of the vector is how much, is a measure of how much they're orthogonal. The magnitude relative to the maximum magnitude. A cross B is orthogonal to both, or perpendicular. I forget a syllable in there. To both A and B. Orthogonal to both, and its magnitude is a measure of how much, let's just write that down. Its magnitude is a relative measure of how much A and B are perpendicular to one another. How effective the turning boost. If it's a rocket and you're firing off another little booster rocket to turn you, and it's kind of 12.25 out of a possible effectiveness of 17.2. Alright, let's go back to the other group, group 2. Any other interpretation, possible meaning of A cross B? And let me open it up to either group, to anybody. Any other possible meanings besides these two?
I think that you can also say that the magnitude of A crossed with B is the area of like the parallelogram.
Yes.
Yeah, that those two vectors form.
Magnitude of A across B is the area of the parallelogram. Don't trust my spelling on any of that. Alright. Now, there's a quick picture that really shows that. This is B. And this is A. Then this, how do you find the area of this parallelogram? Well, the area of that parallelogram would be the same as the area of this rectangle. Because all you have to do is move this triangle over to here and it makes this rectangle. So if we could find this length right here, we would have it. And then we'd say the magnitude of b times this length of this. But this length is, if you take a times the cosine of theta, it gives you this length. You give the magnitude of a times the sine of theta. So this right here is the magnitude of a times the sine of theta. So the area of the parallelogram is equal to magnitude of a times the magnitude of b times the sine of theta, which is a cross b's magnitude. Alright, I think we've got all the relevant interpretations of the cross product here. It's a vector whose itself is the direction, it's orthogonal to both, and it's the rotational force could like screw in a bolt in that direction with the right hand rule. And alright, so now that's A and B. Let's go to C. And let's change this to dot product. So, and let's call it C. Find the dot product of A cross B, and let me copy these over again so we can see them more clearly. All right, 30 seconds, because these go really quick. Alright, so this is, you just take 2 times 3 is 6, plus 4 times 1 is 4, plus 1 times 2 is 2, and you get 12. And then D. State a possible meaning. And the answer you got for a dot B. And as you're feeling so moved, confident enough, do another possible meaning. And as many as you can think of. Yes, it's ready to come up. No. Excuse me. Alright, if you haven't already, type in the answer you got in your group chat, and we'll go over all the possible ones that we can think of. Alright, we'll start with group 1 this time. Possible meaning of this 12.
I didn't quite have time to type it in, but I think the dot product can be thought of as the length of one vector times the length of the projection of the other vector on that first vector.
Length of, and it doesn't matter which one. Length of B times the length of the projection of A onto B. Okay, let's go to group 2. What's another possible meaning of this 12? We had to do something about this. This is the absolute value of A dot B is this. Group 2, you can say pass. Any possible meaning of the dot product?
Nothing that's ultimately different from what was already stated,
Okay,
although it was less specific.
okay. Anybody else can think of any other possible meaning?
I just say simply, so that's one way to find out the angle between two vectors.
A way to find theta, the angle between the vectors A and B in standard position. This is a nice little formula. Cosine of theta is the dot product divided by their magnitudes, multiplied together. Okay, anything else?
I have a off-topic question. Will we ever need to know, like, be able to do stuff with vectors that aren't in standard position? Like, will we ever come across that kind of test?
Yes, you'll get applications where they're not in standard position, and then you got to deal with that. You'll also have times when you want to move them not in standard position, like when you want to add two vectors. When you subtract two vectors, generally you want them in standard position. It'll go from the tip of one to the tip of the other. When you add two vectors, you usually put tip to tail, and you move them non-standard, and then visually you can do them. Yeah, so there are times, yep, when you want them in non-standard position. And you have to work with it that way.
Question?
Yeah.
Yes, so you mean that standard position is one is a horizontal and the other one might be the vertical or
No.
in between with angles?
No. Standard position means the tail is at the origin. So,
Okay, then in that case, the vectors will be the same vector as long as its the magnitude and directions are the same. So if they are not in standard position, we can move the vector around without change magnitude and the direction. So everything, literally most of the vectors we can put back in the standard position, can we?
yes. Generally speaking, we definitely say this vector is the same vector as whether you have it over here or over here. It's the same vector. You can move it around wherever you need to, however is useful to you. Pairs of vectors. There are situations where the most important thing is just how these vectors relate to one another. And when that's the case, then the angle between the two vectors is the big deal. And then you might even rotate them. And then you might even put this vector horizontal and have the other vector up there. And then, like if you're doing a projection of one vector on the other and you're just finding the magnitude of it, it doesn't matter then whether this one is at about a 45-degree angle or it's sitting on the x-axis and so on. So there are times when we do that. There are times we like to do that and rotate the pair together so that it's more easy to see the cosine of the theta is the horizontal component and the sine of that angle is the vertical component and so on. But you generally can't rotate like that unless you have a pair of angles, and the only thing that's really important is the relationship between those vectors. And there's another interpretation. Anybody else want to come up with another interpretation of this? All right, well, let me give it. It's very similar to one we put already up. The relative measure of how common the direction of the two vectors. The closer A dot B is to magnitude of A times the magnitude of B, the more they point in the same direction. Another way to state this is it's a measure, kind of a relative measure, relative to this maximum, a relative measure of the efficiency of the speed boost. Just like the cross product is a relative measure of the efficiency of the turning boost, this is a relative measure of the speed boost. Over here. The bigger the number, the better the speed boost relative to this maximum. The bigger the number over here for the cross product, the more efficient the turn boost is. So, and they're just opposite. Where one maximizes, the other minimizes, so on. Okay, and I have another question for y'all. This one, cross product, had a geometrical interpretation of an area of a parallelogram. Does the dot product have a geometrical interpretation? Anybody want to take a guess? All right, the answer is no, not that I'm aware of. So, cross product got this great geometrical interpretation. The dot product, no. We usually don't see a geometrical interpretation of that one. There probably is. Maybe I haven't been exposed to it, or maybe nobody's really figured it out in a way that makes sense to common people studying this. But there's none that I know. All right. Give me a little feedback on this question number 1 in totality now, with dot products, cross products. Was this useful? What part was useful, if it was, and so on. Okay. All right, let's go to number 2. Without using any technology, no calculator, no computer graphics, anything like this, graph x equals 2 cosine t, y equals 8 sine t, t between 0 and pi. Okay, 30 seconds more. All right, if you were doing this, and having to put a t in here, and putting, 0, pi over 4, and stuff like that, then you probably didn't finish. I didn't give you enough time for that. There's a lot more efficient way to do it than this. I think somebody's got their mic open. Check to see if your mic's open. And the more efficient way is if we take, I'm going to pop over into Discord. Cameron, could you mute your mic, please?
I'm sorry about that.
All right. So the much more efficient way is when you see sine and cosine, as long as the angles are the same, turn this equation into this equation. How do I do that? Well, cosine is not squared. You got to square it. But then it'll have a 4 that's extra. Divide it out. Now this matches that. And then the sine has to be squared, but then it'll have a 64. So you got to divide by 64. And then you get 1. And so this, if these were identical numbers, you'd have a circle. If they're not identical numbers, this is an ellipse. And if you make x 2, it's the biggest you can make the x. Because if x is like 3, you're going to get a number bigger than 1. You can't add a positive number to a number bigger than 1 and get 1. So x is confined between negative 2 and 2. Similarly, y is confined between 8 and negative 8. And then the shape is this ellipse like this. Okay, a little bit of feedback on number 2. Okay, so this was a problem for a few of you on the homework for 14.1 parametric equations. I put a comment saying, because there was a problem similar to this in the homework, and a number of people graphed it without changing it to a Cartesian equation. So you weren't using the efficient way to do it. And that's what I was kind of trying to get you to see when I was asking that question. You know, how did you come up with that equation? And this is kind of where we'd like to go with these parametric equations, is being very efficient with them. Get them into familiar territory when we need to graph them. Okay. And number 3, state the definitions. Dot product, cross product, and their shortcuts for evaluation. It should go very quickly. I'll only give you a quick minute here. Okay, so for dot product, A dot B, its definition is this. For A cross B, its definition is this, times n, which is a unit vector in the correct direction. That's perpendicular to both of these via the right-hand rule. And so these are the definitions. Now the shortcuts. How we evaluate them is a B is A1, B1 if it's in 3 space. It could be in 2 space or more, 4 space, so on. But typically we'll be doing 3 space this semester. And A cross B, we use this. Now the cross product we can't do in 2 space. We have to do in 3 space or higher. But you can do 2 space ones. You just make the 3rd space a 0, and then you still use this IJKE. And then A1, A A3, the three components of vector A, the three components of vector B. And if you give me a little feedback on this, so I know whether I'm kind of like wasting my time or is this good to review this stuff too. And let's pop back over here. So, questions on homework or anything else? All right, no questions on homework. Let's start into today's lesson then. So, dot products and cross products. Let's look at understanding the shortcut for the cross product. Because we give this cross product shortcut, it's really this. This one up here is a quick, easy way to remember, because like in A, in I, it's going to be A2B3 minus A3B2. Just remember that for a second. A2B3 minus A3B2. That's exactly what's showing up here. A2B3 minus A dot B. Alright, so we have this picture of this, and this has to do with the definition. This magnitude times this magnitude gives you the area of the parallelogram. But what the hell does that have to do with this, which is really what you'd get if you did this shortcut right here. And so that's what we're going to investigate today. And you might be happy to hear that there's no additional homework today. Today is kind of like just a consolidation day and try to get some of the whys answered of this stuff. So we're not doing a new section. All right, we'll investigate this. So in order to do this, we're going to take two vectors, A and B, and we're going to have the I coordinate along the x-axis zeroed out. And I'm going to ask you to find A cross B. So let me give you a minute to do that. Find the cross product. Kind of interesting to see what's the cross product of something that doesn't have an x-coordinate. Its x-coordinate is 0. So it's totally on the YZ plane. So let me do it now. It's A cross B. Now J is going to have a column that's all zeros. So this is just going to zero out. Same thing's going to happen with K. So all you're going to get is, what, 12 minus 2, 10 I. Now, let's look in a kind of a three-space visualization. So, if we were in a physical classroom, the blackboard would be in the YZ plane. The X coordinate, the X-axis is coming in the upper left-hand corner or lower left-hand corner of the room out towards the students. And on the blackboard, up here, we have these vectors, 3, 2, and 1, 4. So imagine vectors coming out to here and up to here. And, well, let me actually draw. But they're on the blackboard. And a vector that's orthogonal to both is going to be along the x-axis, 10I. And if I use the right-hand rule, my right hand going from the first one, 3, 2, to the second one. So here, A, B. My thumb would be pointing in the direction of the x-axis. So I get 10I, that's the vector in this direction. That's the resulting vector, way out to 10. That's the cross product of those two. So it's easy to visualize this. Yeah. Now let's go to number 2. How does the I component of A cross B change when A and B are changed to these? Now the A is the same vector that it was before, 3 and 2. But now it has a non-zero x-coordinate, and B is the same vector as it was before, with 1 and 4 as its second two components, but its first component now is non-zero as well. But we only have to find the I component of A cross B. So, how does the I component of A cross B change when A and B are changed to these two? Let me give you a minute to get this. Okay, and when you get an answer, type it into your group chat. And group 1, what do you have? How did the I component change?
I think that the I component doesn't change at all. It remains to be 10.
Because you wind up crossing out its common row, and so this was in its, so it has no effect whatsoever. So we're only interested in the I component. You're still going to get 10I. So it doesn't change. Now this is something very significant. The I component of A and B is totally independent of the X coordinates. The X coordinates don't play any role in determining the I component of A cross B. The I component is really the X coordinate. X coordinates don't affect X coordinates of the result. What we're saying here is pretty profound, pretty significant. Okay. Any questions? All right, the next part is a little bit more lengthy. Let's take a break here. Let's start again. In 15 minutes at 6:42 p.m. And before I take my break, does anybody need to speak to me individually? Yes. Cross product in a 4x4, you use, I think, no, I can't remember for sure. I cannot say for sure if that same little shortcut works in a 4x4. Good question. All right, let's get started again. So the vector that we looked at last time, these two vectors, 5, 3, 2, 3, 1, 4. Let's focus on only the I component of the result. If we zero out the I components and imagine and examine A cross B, we've already done this. That was the first question that we had here, with zeros in the X component. To find the cross product is to find the magnitude of the torque. So we ask, what is the rotational force that 0, 1, 4 exerts on 0, 3, 2? Hold on a second. The way I'm doing it is the second one is the force. All right, so Matthew, maybe the way the book was calling that, how they were putting the force second, maybe that's right.
Yeah.
It seems to be consistent here with what I was putting in here before, so I was remembering it wrong earlier. What is the rotational force that the second vector exerts on the first vector? It is the magnitude of this rotational force that will become the coefficient of I in the cross product result. So now I can draw these. 0, 3, 2. So 3 over and 2 up. And this must be 3 over right here. And this must be 2 up. And this must be 1 over. And this must be 4 up. Okay, so we can see this. What's the rotational force that the B exerts on the A? Does B cause A to rotate clockwise or counterclockwise? Well, it's pretty easy to answer. It looks like it's because the rotational force is the part that's perpendicular, and it's moving in this direction, and now this is what we call counterclockwise, and it's also the positive direction in trigonometry. Remember, we had a 0 angle here and a 30-degree angle, and as the angles get bigger, we go in this direction, counterclockwise. That's the positive direction. So in the YZ plane, so it's kind of convenient. We zeroed out the X. Remember, if this was the chalkboard, if we were in the physical classroom, the X comes out towards the class, and the board itself is all on the YZ plane. In the YZ plane, A is 3, 2, B is 1, 4. Let's imagine B, the vector B, as a fan pushing air, attempting to rotate arm A. If B is parallel to A, then no rotational force is generated. So if the fan is pushing on, you think of this arm as kind of like a plank of wood that's kind of thin and kind of, 4 inches wide or something like this. So, and if the fan is parallel to A, it doesn't rotate at all. B has optimal rotational effect when it is perpendicular to A. Now imagine B as a combined effect of 2 fans, one horizontal and one vertical. Clearly the vertical fan, so B is two fans, a horizontal fan and a vertical fan. The vertical fan is 4 times larger than the horizontal fan. Next, imagine arm A is being composed of 2 arms, one horizontal of length 3, and the other vertical of length 2. The horizontal fan in B, so this little green one, the horizontal fan in B has no rotational effect on the horizontal arm of A. And like with the vertical fan, and the same with the vertical fan, the same is true with the vertical fan and the vertical arm component. So we ignore these. So there are 2 fans, and this arm that's being rotated has 2 portions. We've replaced this plank with 2 other planks of wood. So B, part 1. Find the amount and direction of rotation caused by the vertical component of B acting upon the horizontal component of A. So, let me give you a minute to get the answer to B, part 1, looking at the picture. And work individually for a minute, and then I'll tell you when you can type in your answer to your group chat. Okay, if you got any kind of answer, type it into your group chat. Okay, group 2, what do you have for part B? B, part 1. Group 2, you can pass. But what do you say?
I'm still working on it, so
Okay.
anyone else has an answer? I think maybe Cameron does. He said the square root of bj squared plus ai squared.
EJ.
I don't really know what
What's
that means.
EJ and AI? Cameron? Not sure what that means.
Isn't B isn't B vector B
Yeah,
and A vector A?
right. And B?
Do they not have horizontal and vertical components?
Right.
So I know that using the Pythagorean's theorem probably isn't going to be close enough. It's not going to do it, but that's I'm taking the vertical of B and trying to work with the horizontal of A.
Okay. I think there's a tendency on this one to have a hard time with the language. And but if we look at it the right way, it can become really simple. All we're looking at is this. What effect does this have on this?
The horizontal.
Is it gonna rotate that? Is that gonna rotate this? Now you imagine pushing this green vector, the long green vector, to the end, so it comes at the very end point. The fan gets pointed at the end of this arm, which is a plank, and
Counterclockwise,
it'll turn it counterclockwise.
which I had already mentioned.
So should it be positive or negative?
Positive, because that's the way the unit,
Very good.
because that's how the unit circle rotates,
That's how
cycles.
the unit circle rotates. Perfect. And what should the size of that be? This is 4 and this is 3. So what should we do with the 4 and the 3? We could only multiply them if all the energy of this goes into turning this. But that's exactly the case when they're perpendicular like this. So it'll be the torque, the magnitude of this, times the magnitude of this, times the sine of the angle. The sine of a 90-degree angle is 1. So it's just going to be 4 times 3 is 12. 12 counterclockwise. So that's the amount and the direction of rotation. The amount is strange with these units. If we think of this as like, 3 meters, and this was a force of 4 newtons, and then, you'd multiply them together and so on. But since they're perpendicular, they just multiply. Okay, so now B, part 2. Find the amount and direction of rotation caused by the horizontal component of B acting upon the vertical component of A. I'll give you a moment for that. Okay, type in your answer to group chat. Group 1, what do you have for this?
Let's see, I think it's 2 in the clockwise direction.
Okay, how'd you get to 2?
Okay, so let's see, the vertical component of A is 2, and the horizontal component of B is 1. So, and since they're perpendicular, we can just multiply. Yeah, that's how I got 2.
2 in what direction you said?
I think it's clockwise.
Clockwise. Alright, so you imagine this green is pushing up in the air. So it's going to rotate us in exactly the opposite direction the other one was rotating. And so, thus, we're going to get negative 2. That is the positive direction. This is the negative direction.
So are we only looking at, or are we trying to predict where A is going to rotate, or are we just trying to predict where various parts of, whether the horizontal of A will go this direction or that direction, or the vertical of A will go this direction and that direction? Because if we're trying to find the rotation of A, wouldn't we not factor in the two torques that we've already calculated and say -2 plus 12 gives us a torque of 10?
How did we get... Oh, okay, put both of these together then. You're saying put these together to get the torque of 10.
Yes.
Yes, that's what we're going to wind up doing. We're going to wind up adding these two parts together. All right. Now, this is not the usual way that we would compute torque. The usual way we compute torque between A and B would be that we would, let me go to blue, let's repeat this picture over here.
Tip to tip.
We would this B it's supposed to be more straight up. Let me get that a little bit better. Hang on a second. I think I started it out right. Okay. So we would take this B and we would take it to here. So if we're asking, does B cause A to rotate, we would say, oh, yes, it's causing it to rotate like this. And we would say that this is the magnitude of B, if this is theta, times the sine of theta. For this. And then we would multiply this times the magnitude of A and get the amount of rotation. We'd answer this question in this way, is we would say the rotation is magnitude of A times the magnitude of B times the sine of theta. But that's also the same amount of rotation, and it seems crazy, but is if you had this plank being affected not by one fan, but by two fans. And the vertical component of this has no effect on the vertical component of this, so it's only going to take the vertical component of this fan on the horizontal component of the plank. And then the horizontal fan over here has no effect on this plank, but it has all its effect on this plank. And these two fans, both pointed at the ends of the planks that they affect, is going to have the same overall rotational effect as one fan here pointed at the end point of this plank right here. So if we blew air this way with this, it would rotate us counterclockwise. These two fans are going to wind up doing the same thing. All right. It's a little bit abstract. Give me a little feedback here. Are you following this idea with the two fans and the one fan, or is it too confusing? Give me a little feedback in the main Discord chat. Okay, so let me review it a little bit and then we'll move forward, but let's back up a little bit. Thanks for the feedback. Alright, so I am taking a fan in the direction of B and trying to use it to turn this wooden plank that is, let's say, very thin wood but 4 inches wide. So when I hit that wooden plank with the fan and I aim the fan itself, this pretty powerful fan, at the very end of this plank, it'll cause it to rotate in this direction. And that amount of torque that I would get from that would be this. It's a normal way we would compute it. But it's also true, and this part is really strange, is that if I broke this plank up into 2 separate planks and had this fan, now this fan, think about this fan for a second. Just one big powerful fan. This is going to be replaced with 2 fans. The vertical fan is 4 times as powerful as the horizontal fan. But if those 2 fans were both pointed at the same spot simultaneously, together they would produce this kind of force. All right, so we've broken up the big fan, replaced it with these 2 other fans. Now we also, the effect on this one arm or plank is the same as the combined effect of the 2 fans on the 2 replacing flanks, the horizontal and vertical component of this plank. And when we do everything horizontal and everything vertical, the advantage of that is horizontal fans don't push horizontal planks, they don't turn them at all. Vertical fans don't turn vertical planks, so we only have 2 components to concern ourselves with. How much does the vertical fan turn the horizontal plank? How much does the horizontal fan turn the vertical component of the plank? And then we put them all together and we get this. What's the total rotational effect of each component of B on each component of A? We add them together. The 12 plus the negative 2. They're going in opposite directions. The big fan is pushing us in the positive direction. The little fan on a little arm is pushing us in the opposite direction. And notice we get exactly the same answer, 10, that we got when I took this cross product way back up here. We got 10i. That was the rotational effect right here. And actually, this expression should be, see, if we replace this B with B1, B2, and the A vector with A1, A2. Now, when you took the vertical component of B, that's B1. No, that's B2. Multiply that times the horizontal component of A1, of A, which is A1. That's going in the counterclockwise positive direction. Then the other one is the horizontal component of B multiplied by the vertical component of A, but that's going to send you in the opposite direction, clockwise, which is the negative direction. Now we actually write them like this, A1, B2 minus A2, B1. It's the same thing. But this is the kind of computation you'd see in the cross product shortcut that we had written out way back up. Where was it? Cross product shortcut. Let me find it. Right here. these kind of things. A1, B2, A2, B1 was the third component in this. So where does this, so it becomes this, where does this show up? Where does A3B2 minus B2B3 show up in A cross B? It's the very first component in A cross B, as we were just looking at. Alright, so now number 4. Let's go back to A and B. Now these are when you don't have zeros as the first. So this is the real A and B that we were going to be looking at. Let's zero out the Z components this time. So I'm going to ask you to do the following. Draw your usual two-space version of an XY coordinate system. And we'll imagine a Z-axis pointing straight up. So you're going to write, let's imagine that we're writing on a horizontal paper. It's probably on our desk, but we can imagine that it's on the floor, and that the floor is the XY plane, and then the Z-axis points straight up. And then show the visual interpretation of those two vectors, visual interpretation of this cross product. We actually want this, and explain with two fans and horizontal and vertical arms. So let me give you a little bit of time to draw this and explain it. So you're going to kind of repeat the process that I just created. This time you're going to create it with the Z component zeroed out. Excuse me. Okay, so I'm going to ask for a volunteer who would kind of lead me through how I might get started on this. Anybody? Want to volunteer?
I would be willing to volunteer.
Okay, X and Y. So I'm going to 5 through put 3, 1. We'll make one of them blue and the other one blue. And imagine the z-axis is turning up and speed. Okay, so it's growing. What do I do?
Okay, so I think you should first break each of those vectors into components and then draw the components. Yeah.
Okay.
And then we just need to combine the pairs of components that are perpendicular and in different colors. So, like let's do the green one that goes from 0 to 3,
Okay.
multiplied by, so that bottom one, multiplied by the blue one that's perpendicular to that. That goes from 5, 0 to 5, 3.
Okay.
And so, yeah, that one has a magnitude of 3, and that one also has a magnitude of 3. So, like, that pair is equal to 9. And it's going to be -9, because if you put, like, the two arrowheads together, you're going to see that it's going to turn clockwise.
Okay. Great.
And then the other pair of vectors, we've got the long blue one at the bottom, which has a magnitude of 5. And then the small green one, which has a magnitude of 1. And that's equal to 5. And that one's going to be counterclockwise, so positive. Positive 5.
Okay. So this one was this one over here. The horizontal. And then this one over here. And they multiply together. And so this, which one was the force? The green one?
I think, let's say that the green one is the force.
Okay, so it's always the second one that's the force. And that's what I'm saying. So this is the force. And the blue is the arm. Okay, so that force gets placed on this arm right here and rotates it counterclockwise. So it's positive. Okay?
And then you can just combine those two pairs to get like the net effect, and that's going to be -4.
-4, and what's the meaning of this negative?
That's going to be the magnitude of the cross product, but only in one direction, and that direction is going to be in the z direction. And I guess if we use the right hand rule and we go like I think it's going to be positive z.
Okay, and now notice the z component of A cross B is the amount of rotation in the xy plane. So it's really strange. The xy plane we're measuring is the floor. The z component is straight up, or in this case straight down, because it's -4. So using the right hand rule, from the arm to the force, we wind up going straight down rather than straight up. And so the amount of torque in one plane, we know that the cross product is perpendicular to both of those vectors. So if it was in the xy plane, we know the torque has got to be in the z plane. That's exactly what we're seeing, and because it would be kind of like using a wrench on a bolt, and it would screw in a direction perpendicular to the plane that we're working in. And so we wind up getting all this. All right. Give me a little feedback in the general Discord channel where you're following Rowan's explanation. Well, is this making sense? Where are you at? Okay, makes sense to Matt, Cameron, Yulia, Hisu. How's it going? Alright. Might take a while to get this. Might take looking at it all again. I remember lots of times being really lost during a class and having to reconstruct it and go very carefully over it later after class. Alright. Alright. Let's go multiplying 2 by 2 vectors, 2 by 2 matrices with visualizations. Alright. So let's take two vectors, the vector, I'm just going to make up two vectors. 2, 1, and 3, 5. Okay, now one typical application of why we use vectors and why we use matrices with vectors is if you had this situation, if these 2 and 1, were the components of a system of equations, 3x plus 5y equals something else over here. Now these could be like 7, negative 9, any kind of numbers over here. Now, suppose you were solving this system. Now, when are you going to get a single solution? This system of equations has a single solution only if these two components, 2 and 1, which is this vector, only if this and this, 3 and 5, only if those things are not parallel. Now, how do we tell if they're parallel? If one vector is a multiple of the other. So for instance, if this, see this one is 5 times bigger than this one. If this one had also been 5 times bigger than this one, 10, 5, then these two vectors would have been parallel. This would have been 10x instead of 3x. And then we would have had, when you tried to solve by substitution or elimination, if you tried to multiply both sides by -5 up here, all the variables drop out, and you get, it turns out the two lines are either on top of each other, which has infinite number of solutions, or they are parallel to each other, which means you have no solution. The only way you're going to get a single solution is if these two vectors are not the case where one is a multiple of the other. It doesn't have to be a whole number multiple, it could be a fractional multiple. All right. Now, when we take the determinant of a 2 by 2 matrix, we are going to get 10 minus 3 which is 7. This determinant will be 0 if this is the case, if one vector is a multiple of the other. Let me demonstrate. We said 2, 1, this one 5 times bigger than that one, so if this one was 5 times bigger than that one, we would get this. 10 minus 10 is 0. If these two vectors are multiples of one another, you will always get 0. And it's kind of a hidden feature in the determinant, is that the determinant has to do with the system, corresponding system of equations. And if the determinant is 0, then you're not going to get a single solution. You'll have one of those exception cases, like parallel lines or lines on top of each other. All right, now, how come parallel lines always give you this, a determinant of 0? Well, just think, if these two, so A1, A2, those are the two components of the first vector. Suppose the second vector with some constant, I don't know, k, times A1. So instead of calling it B1, we're saying it's a multiple of this. K, A2. So if this vector is a multiple of this vector, now let's take the determinant. We're going to get, when you multiply across here, you get k times A1, A2. Multiply across here, you get k, A1, A2. You're going to get 0. Okay. Even further, to demonstrate the point further, if one vector is a multiple of the other, then when you take one vector being a multiple of the other, your these things turn out to be this, but look at the ratio. A1, A2, B1, B2. Another way to look at it is, one vector is going to be a multiple of the other. Multiples if the ratio, this to this, is the same as this ratio. So that would be, in this case, 2 to 10 is the same as 1 to 5. They both reduce to 1/5. That tells you that they're multiples. Okay. Now, when you take this cross thing, when you take A1, A2, B1, B2, and you take the determinant, you're getting A1, B2 minus A2, B1. And if it's 0, then that means that, you're not going to get a single solution. But if that's 0, that implies, let's move this to the other side, A1, B2 is equal to A2, B1. Then let's divide both sides by B1 with B2. That will imply that now these guys are going to kill each other off. A1, B1. These two are going to kill each other off. There's A2, B2. If the determinant is 0, then the ratios were equal. The determinant being 0 kind of hides the essential characteristic that what it means. And unfortunately, the way math gets taught these days, we often gloss over these things, and instructors just say, well, this is the case. If the determinant is 0, then the vectors are, parallel. But they don't show why any of this stuff is true. When I was getting my own education, I got the same type of education. I got, here's the facts, but no explanation about why they're true. And so all of this I had to kind of work through myself to figure out, okay, that's why it's this way. I had a really difficult time remembering things if I didn't understand why. So for me, there wasn't much choice. I had to kind of just keep pushing till I figured out why. It was a weakness that I couldn't memorize something, but it turned out to activate a strength that, I could figure out why it's true. It's often the way life works, is that our weaknesses are the activating force that develop a strength for us. So then, now, multiplying 2 by 2 matrices, the determinant, we wind up like this. Okay. Now, when you take the determinant, notice you're always taking these determinants when you're doing these cross products. This shortcut for this visualization. When we did the very first one, we got all these determinants of 2 by 2's. The I was the determinant of the 2 by 2 over here. Now, these determinants of 2 by 2's also have this other meaning. Now, what's really fascinating is this theory all extends to 3 space as well, and the determinant of a 3 by 3 matrix. Now, it's much more complex, but when you get that number, it has that same interpretation of the 3 different, now they're not equations of lines anymore, they're equations of planes in space. But the 3 planes in a 3 by 3 would be, would give you a single solution, just like if you took the plane of one wall in your house and then a perpendicular wall in your house, 2 vertical walls that are perpendicular, they meet in a line. And then if you intersect that with the floor, you get 1 point. The intersection of 3 planes can be 1 point, but it won't be a single point if 2 of the planes are parallel, or if 2 of the planes are on top of each other. And you could get infinite solutions or no solutions. And it all extends in higher spaces. And these determinants. So let's continue on with this. There's another thing with we had these 2 vectors, 2, 1, and 3, 5. Let's take these 2 vectors again, 2, 1, 3, 5, and write them down. Let's look at the visualization. Two, 1, 3, 1, 2, 3, 4, 5. We'll put 1 in blue, 1 in black. Now, when you take the determinant of this matrix, you're going to get a number, 10 minus 3, which is 7. That number is the same as the area of this parallelogram. Right over here. And it's the determinant gives you the area of the parallelogram that's in 2 space. If we were in 3 space and these were 3 different vectors, we would wind up getting, and we took the determinant of that matrix that comes from putting the 3 different vectors as the 3 different rows or the 3 different columns. You can do it either way. The determinant of that would wind up being the determinant of what's called a parallel pipette, where if you had another dimension, let's say a vertical going up, then you could make a 3-dimensional with a parallelogram as its bottom and top, and 3-dimensional side, and so on, and then you find the volume of that, and that's what you'd get as the 3-dimensional, the determinant of that. Now, this right here, when you're taking this, let's look at what's happening, another perspective on this. These 2 vectors were placed to make the 2 rows of the matrix, and then we took the determinant. Now, when you're taking the determinant, you're taking the x-coordinate of the first vector times the y-coordinate of the second vector. 2 was the x-coordinate of the first vector. And then 5 was the y-coordinate of the second vector. And when you multiply those 2 together, you get this area. Now, let's look at this one. 3, 1. Now, when you take this area is bigger than the area of that parallelogram. you take the 3 and the 1, and you multiply those together. Let's do those in red. The 3 is the x-coordinate of this point up here. And 5, no, the 1 is the y-coordinate of this one here. And then when you multiply those together, you get the area of this. And if you take the area of that, subtract the area of that, you wind up getting the area of this. It's not at all obvious. You can't see that that's true. But it does turn out to be a fact in this. And the area of this thing, of the parallelogram, we would normally find the area of this parallelogram by doing what? The magnitude of this times the, you take this one down, straight down, perpendicular to this, okay, and then you multiply these two together. So the magnitude, so if this is A, and this is B, we would take the area of the parallelogram, is the magnitude of A times the magnitude of B, times the sine of the angle in between them. And that's clear from the picture. But what we also see is this is the A cross B, the shortcut. And the A cross B is we would have to make these into three-dimensional ones, putting a 0 as the 3-space coordinate. If you did that, you'd get 2, 1, 0, cross, 3, 5, 0, and then you do the I, J, K, I times, and then it's going to be 0, 0, 1, 5, it'll 0 out. The J will also 0 out. But the K will be the only non-zero part. And this will be 10 minus 3, 7, K. So we see that the magnitude of this is 7, which is the area of the parallelogram, which is also the determinant of the 2 by 2 matrix. And we start to see some big-time connections with some of that. And there's a lot more in almost everything that you get taught in math. There's way more that goes beyond the limited amount that you get taught. And researchers have examined the way that math gets learned, and there used to be this model that was used that people would talk about. They would say, this is how math is. You learn this much, and then later you learn this much. And concentric circles. You keep getting a wider and wider view of mathematics, and you learn more and more. And this is how mathematics is learned. But when the researchers said, how is it really learned, is you wind up learning a little bit, expanding out, maybe expanding out a little more, and then you wind up retreating back because you'll learn something that tells you, oh my gosh, these things that I used to do before had so much more involved with them than I thought. And the circles keep expanding back and forth, and some of the simplest things you learn have wholly new insights when you see them in other relationships and other contexts. And then it's expanding in and out, back and forth. And we are out of time, and there is no homework today. If you got lost during parts of the presentation today, I would say probably the majority of you got at least lost in at least part of it. Feel free to go back and learn more about it. If you don't, it's not like specific homework though is dependent on this. This is just new insights that hopefully will add some depth to the learning. And if parts of it are confusing to you and you never resolve it, you could well still be okay with that. And we will stop here. Any questions before I stop? All right, let me stop the video.